of the semester we'll be doing circuits. Chapter 5 we'll get into magnetic fields, but just for a short time, and then we'll segue again into circuits, because we need to get into magnetic fields to understand how we get alternating circuits, inductors and things like that. So in chapter 3 we'll see current and resistance. Those of you in lab have already seen this. And then in chapter 4 we'll see resistors in series and parallel. Again, those of you in lab have already seen that, but we'll do it a little more detail. And then we'll do multi-loop circuits in chapter 4. You haven't seen that, those of you in lab or not. If you're not in lab, don't sweat it. Listen, we'll master it in this class. And then in chapter 5, we'll move into magnetic fields. That'll probably be the next exam, chapters 3, 4, and 5. Chapter 3 is really short, just take us a couple of days. And it's really combined with chapter 4, just to define a few things. All right? Let's begin with chapter 3. So in chapter 3, I said we're going to define current, we'll see Ohm's law, and we'll define resistance and power as well. We'll see those ideas come up again in chapter 4, but we're just going to define them here, lay them out. So current is the rate at which charge flows past a point in a given time. So the electrical energy that we transfer to the wire is transferred in this form of current, where these charges actually flow through the wire. And the current, which we call I, is defined as the charge divided by time. Anytime we talk about a rate, it's usually a time rate. Not always, but usually it's a time rate, so charge per unit time. The unit for current is the ampere. I think there's an accent somewhere, but an ampere, 1 ampere, we abbreviate it in a couple different ways. You might see it abbreviated as 1 amp. You've probably seen that before. Or maybe as 1 amp in that way, 1 capital A. And the basic SI units are 1 coulomb per second. So remember, a coulomb, that's our fundamental, or that's our unit for charge. And if you recall that 1 electron has a charge equal to 1.6 times 10 to the minus 19 coulombs. That was our fundamental unit of charge, actually the negative of that value. So that is our fundamental unit of charge. The conventional direction for current is the direction that protons would flow. However, we know that in conductors that it aren't the protons that move. If we think about a conductor, you know, we have protons in the conductor that are tightly bound, and then we have electrons, which we call conduction electrons. You know, some of the electrons are bound tightly to their nuclei, but the conduction electrons are allowed to move freely, mostly freely, throughout the conductor. So these conduction electrons will move in response to an electric field. So we're actually setting up an electric field within this conductor, and we're causing these charges to feel forces, and they move in the direction, or actually in opposite direction of the electric field, because it's a negative charge. So then, why do we then assume the conventional current for direction to be the direction that protons flow? Any ideas about that? Why would we assume proton flows, not electrons? Protons aren't moving, but we're going to assume that. Any ideas why that might be? No. Well, it has to do with history, and Benjamin Franklin, he's the one that really did a lot of the pioneering work in electricity, and you know, a lot has been done since, but he did a lot of pioneering work in electricity, and he thought at the time that protons moved, not electrons. He just didn't really understand the atom and how it was set up, and so he thought that protons moved, not electrons, and because of that, he said, well, these positive charges are moving through the wire. It's not really going to affect anything that we do, except that when we draw a circuit, we'll always assume that our current flows off of the positive side of the terminal. I like to imagine that I have this positive charge and it's repelled away from the positive side of the battery. All right. You can also think of it as this is my high potential side of my battery, and this is my low potential side. I mentioned this back when we first drew the symbol for the battery. This is my positive, this is my negative, this is my red, this is my black, this is my high potential side, this is my low potential side. And if you remember, when I have a positive charge, it's going to move from high potential to low potential, like it rolls down a hill. Moves from high potential down to low potential. And so in a similar way, we'll assume our direction of our current to be in that way, moving from high to low potential. So positive charges are repelled by the positive terminal. You can think of them as being repelled. Really, you want to think of it as sort of rolling downhill like this, moving from high to low potential. But if you want to think about being repelled and being attracted to the negative terminal, then that's just fine too. All right. It's not terribly important, but it's sort of important as we deal with circuits that we're all on the same page for this. All right. We're going to have a little bit about ammeters and voltmeters, and you guys dealt with this more in lab, but there are a few things that I want you to know about ammeters and voltmeters. So first of all, what you use to measure them with, you use an ammeter to measure the current. The ammeter is hooked up in series. So if I were to take this circuit and I wanted to measure the current in the circuit, I would put my ammeter right here. That would be in series with the resistor. And whatever current is going through this ammeter is also going through the resistor. Now a little bit later I'm going to show you Ohm's law, but let me go ahead and show it to you right now. We can determine the potential across something is equal to the current times the resistance. And many of you have already seen this in lab. But the potential is equal to the current times the resistance. So we want our ammeter to alter the circuit as little as possible. In general, when you make measurements, that's what you want to do, to alter the system as little as possible. And that can be quite difficult. So with our ammeter, what about the resistance, whether it be big or be it small, what about that will make it affect the circuit as little as possible? Do we want our ammeter resistance to be big, or do we want it to be small? We want it to be very, very small. And if the resistance of our ammeter is very, very small, because my resistance is related to my potential in this way, if I have a small resistance, then I'll have a small potential. Now the current is what it is. Whatever current is flowing through this will go through the ammeter and the resistor. But if we have a very small resistance, then I'll have a small potential change across the ammeter. So we want our ammeter to have a very small resistance. It has a small resistance, so a very small change in potential across the ammeter. And this changes the circuit as little as possible. You learned in lab, and you're not responsible for that for this class, but you learned in lab also that the ammeter consists of a galvanometer and a resistor, remember, and that resistor was in parallel with the ammeter, and it's a very small resistor. That was called your shunt resistor. But not responsible for that for this class. I think we're getting to that. Let me see. No, we're not getting to that. So to measure the voltage in a circuit, use a voltmeter. Some of you might have used actually what we call a multimeter. That's the little palm device that has the two electrodes, or the two leads that come out. You put the leads into your circuit, and that can act either as a voltmeter or as an ammeter. If you haven't used one of those, you've probably seen one before, and you'll probably use one at some point in your career, especially you chemists, especially, or any of you, all of you actually, as you go and you deal with technical devices. You'll probably use a multimeter at some point. Electricians use them a lot when they're repairing electrical devices. So anyway, to measure the voltage in a circuit, use a voltmeter. It is hooked up in parallel. So if I wanted to know the voltage across this resistor, I would hook up my voltmeter like this. And it would measure the potential between this point and this point. That's why we call it a potential difference. It measures the potential difference between those 2 points. Now, if we think about current flowing through this circuit, it comes up here, and that current is going to split at this junction. We'll get into this in chapter 4. It's something called the junction rule. But the current is going to split at that junction. Now, we want most of the current to go through this resistor. In fact, we want very little current to go through this resistor. The voltmeter has a resistance, but we want very, very little current to go through it. So therefore, should we have a big or a small resistance for the voltmeter? If I want very little current to go through it, do I want to resist the flow of electricity a lot or just a little bit? I want to resist it a lot. So the voltmeter will have a very, very large resistance. The voltmeters y'all use in lab are thousands, like 10,000 ohms. So the resistance of the voltmeter is big. This limits the current through the voltmeter. So you get very, very little current. So you get a small current through that voltmeter. Now, will you get a small voltage across that voltmeter? Yeah? No? Maybe? Well, not necessarily. You're going to get whatever voltage that you have across this resistor, you'll get across this voltmeter. In fact, we'll see later, and y'all in lab know this already, but we'll see later that the voltage here is equal to the voltage here because they're in parallel. Devices in parallel have the same voltage. We saw that with capacitors, actually, right? That they have the same voltage. And then similarly here, whatever voltage is here will also be here. So this voltage might be small, or it might be really big. It's going to be exactly the same as this. In a similar way, with the ammeter, the voltage here is really small because it has a very small resistance. But the current here, it could be small or it could be big. It's going to be exactly the same current as what we have going through this. We'll see that with resistors in series, that they have the same current flowing through them. But you can probably imagine that if I have current flowing through the circuit, whatever charge goes through here is also going to go through here. So it could have a big current, could have a small current, but it will always have a small voltage because the resistance is so small. This is basically a wire. You're basically just putting a wire inside of this circuit, which has practically zero resistance. All right, let's try this quick test. Easy peasy, sort of a practice. All right, just a few more seconds. Let's like this, everybody. We'll stop at 20. All right, very good. A is right. Hey, a little geometry for you this morning. Well, let's do this one, and then I'll give you a little bit of geometry. Which of these statements is always true? The current through an ammeter is small, or you can read it. Which of these statements is always true? All right, let's stop at 50. So a few more seconds. Two and three. Yeah, the current through the voltmeter is always small. The voltage across an ammeter is always small. The current through an ammeter, just think about this, the current through an ammeter, it's going to be the same as what's in the circuit, right? It can be small, it can be big. The voltage across the voltmeter, it can be small or it can be big. Justin? I appreciate that. Thank you. Nobody put D there, so but the answer is B. Thanks, Justin. All right. Let's see. I'll give you that geometry. Do y'all know why obtuse triangles are always upset? They're never right. You know what an obtuse triangle is? Right. What is that? Angled or greater than 90 degrees. All right, let's try this. Or let's look at resistance in Ohm's law. The flow of charge, that is the current, is proportional to the voltage. So I is proportional to V. This shouldn't surprise you because remember voltage is energy per charge. This is a measure of energy. And if I give my charges more energy, then you can imagine they're going to move at a faster rate. They're going to move through more quickly. You'll have a bigger current. So if a battery provides a greater voltage, because voltage is energy per charge, it's going to provide more energy to the electrons. Thus, there's a greater flow of current. So I is proportional to V. And Ohm's law, what this does is it describes this relationship based on a quantity called the resistance. We've seen this a lot where we have one quantity is proportional to another quantity. Bless you. And we just sort of create this constant. And R is sort of like a constant that we're creating that describes how a material resists the flow of electricity. And it's based on the proportionality between V and I. So we define R as V divided by I. So for a material, if R is big, you need a greater potential difference is required to produce the same current. Or required to produce a current. So that's just saying R is equal to V over I. So if I have a big R, then I need to increase my V in order to produce this current. So my voltage and my resistance are related in that way. The unit for the resistance is the ohm. We use the capital letter omega as the abbreviation for that. And usually the way we see Ohm's law written is like this. You've probably seen it like this, is that V is equal to IR. Ohm's law is really a definition of the resistance, but usually we write it like this, where my voltage is equal to the current times the resistance. Remember, this is volts, this is amps, and this is ohms. Guys, if you did this in high school, a lot of teachers make this little triangle. I don't really know. It's like this, right? Is that right? Anybody ever see that before? Yeah, is that right, how y'all did it with a triangle? You did it for power, right? P and V and I. Mass density. Okay. Anyway, if you've seen this before and it helps you, that's great. If not, don't worry about it. Okay? So let's try this quick test. I have this resistor, a certain voltage, over a certain period of time. I want to know the charge that passes through that resistor. All right, let's stop at 135. 135. Just a few more seconds. It looks like we're sort of all over the board here. That's okay, I'll show you. Just putting together a few of these definitions. So we have V equal IR. I want to find the current. That's going to be V divided by R. So that's going to be 2 divided by 10, which is 0.2 amps. So I have 0.2 coulombs per second over a period of 2 minutes. I want to know what Q is. Q is equal to I times T. That's based on my definition of current. Remember, I is Q divided by T. So I is 0.2 amps times 2 minutes, which is 120 seconds. And remember, an amp is a coulomb per second, so my units cancel out to give me coulombs. That's 0.2, that's 24 coulombs. So A is the right answer there. Let's see, C. Oh, I know what y'all did for C. You didn't convert your minutes to seconds. Remember, your SI unit for time is seconds. So be careful with that. You could see a question like this in the multiple choice part. I might actually give it to you in the free response, but you can see one sort of tacked on to a problem where we have a larger circuit. Need to know your definitions for I, V, and R. Could see a little bit about non-ohmic devices and ohmic devices. Really, all I want you to know is that these things exist, that there are other devices that don't follow Ohm's law. For the most part, most of the things that you'll deal with are ohmic. That means that they follow Ohm's law. But sometimes, like if you're dealing with diodes or special chips, like I think Dr. Wayman is beginning to do more circuits in instrumental, where you do higher level circuits. You'll see some other things, chips and what have you. And those things are not ohmic. Materials that do follow Ohm's law are called ohmic devices. But as for non-ohmic devices, the resistance of the material changes as V and I change. So for an ohmic device, as you change the voltage, the current changes likewise. As I increase my voltage, my current changes. And so, for example, y'all did this in lab. I is equal to 1 over R times V. Right? That's just Ohm's law rewritten. So the slope of this graph of I versus V is equal to 1 over R. By the way, do y'all know why I wrote it that way? Go back to 8th grade math or so. Well, maybe it's 8th grade. I plot my dependent or independent variable on the y-axis. Dependent on the y and independent on the x. And usually when you have a circuit, V is your independent variable. You change V, and then the current changes in response to that. So that's why we graph it like that. Though in lab, you had a slightly different setup where they were switched, where your current was the independent variable. That's the thing that you set. Non-ohmic devices, on the other hand, they look like this. Or they can look like this. And notice here that the slope, I have practically zero slope here and infinite slope here. And so my resistance is going to go from infinity to, what's this? Or this would basically be no resistance to complete resistance. Is that right? 1 over 0 goes to infinity, right? Yeah, so this would be a lot of resistance, and this would be practically no resistance at all. So here I have a very big resistance, basically R approaching infinity, because my slope is 0, R is it's 1 over 0. And right here, I have a resistance that is approaching 0. That is R is equal to 1 over infinity. My slope gets really steep, and here R equals to 1 over 0, which is the same as infinity. Did I get that right? Did I get that? Yeah, that's right. The point is here that your resistance changes. That if I have a certain current of a certain value, my resistance can be all on, or if I have it at another value, it can be all off. That becomes useful when you're making diodes, because diodes, the resistance is very small in one direction and very large for a current in the opposite direction. So these act sort of as a one-way valve. They allow current to go in one direction, but then they don't allow it to go in another direction. You've probably seen symbols for diodes. In fact, you've probably seen diodes before, light-emitting diodes. Those use diodes. The symbol for a diode usually looks something like this. Sometimes you got a line in there, but that's a symbol for a diode. We're not going to use diodes at all in this class, but in other classes you might see it. Like I said, I think Dr. Wayman is beginning to do some senior level circuitry work in his instrumental class, which is useful, especially for you chemists, because you'll be dealing with your own instruments and either building your own instruments or at the very least, working and repairing your own instruments in the future. Okay? That was like one of the most useful classes that I had as an undergrad and as a graduate student, was learning about these circuits and how to use these chips and how to just deal with circuits on a breadboard. So it'll be a good experience for you. But this is good sort of ground level work for you. All right? Yeah, in graduate school I took this class. It was called Astronomical Instruments. Y'all would love this. It was a lot of fun, actually. They gave us a diffraction grating, and they said, build a spectrometer. And so we had to machine all the parts. We had to design the optics. We had to use various software to model the optics. And then we had to get a certain resolution. I think we were doing a mercury line. But it was a lot of fun to do, and just you get to learn how to use all these different tools. You might have similar classes or projects when you go into graduate school, or if you go into graduate school. Do you have a question? No. All right, let's try this. Is this device ohmic or non-ohmic? If I put 3 volts, I get a current of 2 amps. When I apply 6 volts, I get 3 amps. Is it responding in an ohmic or a non-ohmic way? All right, let's stop at 50. Okay, this device is non-ohmic. The way you tell is just say, well, does the resistance change? For a non-ohmic device, the resistance will change. For an ohmic device, the resistance will not change. So we say for the first one, the resistance is V over I. That's equal to 3 divided by 2. For the second one, the resistance is 6 divided by 3. So since the resistance changes, it goes from 1.5 ohms to 2 ohms, then that tells us that this is a non-ohmic device. Though with most non-ohmic devices, it's different. It's much more stark, that you go from 0 ohms to an infinite number of ohms. Right? That it goes from a very, very small resistance to a very, very large resistance. All right, let's see. I think I have a video. Let's watch. This is, I think it's a magazine video. Let me pull it up. All right, let's look at resistivity. So we define resistance in a couple of ways. We define resistance as R is equal to V over I. But we can also define resistance kind of like what we did with the capacitors. Remember we had the capacitors? The capacitance was Q over V. And then we also define the capacitance as that epsilon naught A over D based on the geometric properties of the capacitor. We're going to do exactly the same thing with the resistor. That we'll look at the length of our resistor and we'll look at the cross-sectional area of the resistor. And those things we'll find are actually proportional to the resistance. Finally, we'll also look at the material of the resistors. Some materials are just better conductor of electricity, right? Like wood or metal. Which of those conducts electricity better? The metal does. So we'll find that metal has a lower resistivity. That is a measure of its ability to conduct electricity. We can think of electricity a lot like water in pipes. So a large pipe lets a lot of water through. So if I have a big pipe, it's really easy to have water flow through here. So we would say that it has a very low resistance. Whereas if I have a very thin pipe, then it's harder to push that water through. So we would say that it has a big resistance. Given the same amount of energy per unit mass, it's sort of like the pressure that you're using to push this water through, you'll get more water flowing through the big pipe with the low resistor than you do through the smaller pipes with the big resistor. And so with that idea, we can think about that if I have a pipe, how does it affect the resistance? So let's say that we have two quantities that affect the resistance. We have the area of the pipe. That's, this, the cross-sectional area. And then we also have the length of the pipe. So let me ask you a question. If the area increases, what happens to the resistance? Does the resistance increase? Does the resistance decrease? Or does it stay the same? So if I increase the area of my pipe or my resistor, the same idea is gonna hold true here. If I increase the area, if I make it bigger, does that mean that my resistance has increased, decreased, or stayed the same? I'm going to go and write the second question. But answer the first one. I'll stop here in just a couple seconds at 35. Okay, good. A is right. If I increase my area, the resistance decreases. If I make my pipe bigger, it's easier to force water through it. But what if I make it longer? What happens to the resistance? If I take that pipe of a certain radius and I just make it longer, does the resistance, does it increase? Is it harder to push water through that pipe? Does it decrease? Is it easier to push water? Or is it unchanged? Does the resistance not depend upon the length? All right, we'll stop at 32. All right, so if I increase the length of my pipe, the resistance will increase. No reason for you a priori to know that, like we haven't said that before. But if you think about a hose, like y'all ever try to push water through a hose? Like blowing on a hose and try to push water through a hose. You ever try to siphon gas out of a vehicle before? Ever done that? Listen, when I was a kid, we were kind of poor. I mean, we didn't really think we were poor. We weren't like dirt poor, but we were kind of poor, working class. But we would often run out of gas. And so when we ran out of gas, we'd go down to my uncle's house and say, "Hey, can we have some gas?" And my uncle, he's kind of funny, but he had several vehicles, and we would just go out and we'd take gas from one of his vehicles with his permission, of course. And we take a garden hose, right? And you put it down in the gas tank. First you blow to hear if there's any gas actually in the gas tank. You ever done this before? You've done it, right, Tim? Yeah. And then you sort of suck up a little bit to get the gas coming out the hose. And this is the tricky part, because you have to get the hose out of your mouth before the gas gets to your mouth and into the gas can. Or you get a mouthful of gas, and that's happened too, of course, before. I'm sure everybody's happened to you before you had a mouthful of gas. Well, if you do this with a longer hose, like if you have an 8-foot hose, that's going to be a lot more difficult, because you don't use an 8-foot hose. You have a little section of hose that you keep curled up behind your seat just for that purpose. I'm serious. You know people that have done this, and now you know at least one. But you don't keep a big old long section of hose, because the resistance in a longer section of hose, it just has more resistance. It's hard to draw up all that gas into a longer section of hose. It has more resistance. So if I increase my length, my resistance also increases. So already we have two things. We have R is proportional to the area. If I increase the area, or excuse me, not proportional, proportional to 1 over the area. If I increase the area, the resistance decreases. R is proportional to the length. If I increase the length, the resistance increases. An inverse and a direct proportionality. We also describe the material by the resistivity. So the resistance is proportional to the resistivity. So wood, for example, has a big rho. That's the Greek letter rho, by the way. Metal has a very small rho, most metals. Wood resists the flow of electricity a lot. Metal doesn't resist the flow of electricity. It has very little resistance. So we can combine these to get an equation kind of like what we had for the capacitance. Remember, the capacitance was epsilon naught A over D, where we had that expression. We're going to a very similar thing now for resistance, is that R is equal to rho times L divided by A. I have direct proportionalities with the resistivity and the length. If I increase these, I increase resistance. If I increase this, I decrease the resistance. If I make that resistor bigger, then it's less resistant to the flow of electricity. That's probably the hardest thing, because that doesn't really always make sense to us, that if I have a wire that's this small, it has a certain resistance to the flow of electricity, but if I can make that wire this big, then the resistance is decreased quite a lot. And I think it doesn't make sense to us because we think of it as, oh, there's more material for it to go through. But really you want to think of it as, oh, there are more conduction electrons to carry the electrical energy in that bigger piece of metal. That's why the pipe works well, because, you know, you use a big pipe has little resistance. A small pipe has a lot of resistance. Okay, we have time. Let's do these couple quick tests, okay? This first one's kind of tricky. Think about which one is bigger, wire A or wire B, and then also think about how the area is proportional to the diameter. It's not a linear proportionality, it's a quadratic proportion. So think about, first, which one is bigger or smaller, the resistance, or the diameter is bigger or smaller, and then think about by what amount. Right away, you could get rid of option C. Because you know they don't have the same diameter. All right. You think you're doing well on this question. I know, because everybody seems very confident. But I think most of you are, in fact, wrong. In fact, only 2 of you have the right answer. I know that you think you have the right answer, but most of you do not. All right, I'll show you. Let's stop here in just a few seconds. I'm going to stop at 208. 208. So most of you put either D or E. And it is one of those. Most of you put either D or E. So let's try it again. Ask your neighbor what they put. They probably put the same as you, I guess. And then I guess you just put the opposite answer. But why would it not be the answer that you likely think it is? I'm glad that you put D or E, because resistance of wire A is big. That means it's going to have a smaller diameter. So wire A is definitely smaller than wire B. So we can get it down to just 2 options. But how do we figure out the particulars of that? I'm going to stop this at 42. 42. Just go ahead and guess if you're not certain. 45, maybe? All right, y'all go and put in your answers, for goodness sake. All right, 53. All right. All right, what is the answer? It is D. All right, so look, resistance is rho L over A, but my area is actually pi r squared, right? So we're not looking at area, we're looking at diameter, and that's where y'all are getting messed up, is that you said that the area is 1/4, that the area of wire A is equal to 1/4 the area of wire B. And that's true. That is true for this. But notice that we're looking at the diameter. And so the diameter isn't proportional to the area. The diameter squared is proportional to the area. So if I halve my diameter, I quarter my area. So that's where you were messing up. But that's good that you put either D or E. That maybe you put here, that you recognize that wire A has to be smaller than wire B. We'll see that question come up again in some different ways later. All right, this is also a nice question. You'll probably see a question on your test like this, where if you have a metal and you just don't know what the metal is, a very simple way to determine what this metal is, you can look at its color and its density and all that stuff. You can also apply a voltage to it and measure the current, and then calculate the resistivity. So here, what you want to do is first calculate the resistance by Ohm's law, and then calculate the resistivity based on the dimensions of your wire. And y'all did this in lab, but it's a nice way to determine unknown metals. Let's try it out. You have a homework question like this. You'll probably see it on the test too. All right, let's stop in about 10 seconds. I'll go to 220. 220. Just guess if you don't know. It's a few more seconds. All right. Okay, I think D is right. Let's see. So what you do here is you say R is equal to V over I. V is 1.4 over 20. So that's what, 0.07 ohms, is that right? Yeah, and then you say R is equal to rho L over A, and solve that for rho, and you get rho is equal to RA over L. And you have the values for area and length, 1 meter, and you solve for the resistivity. And you find the resistivity is equal to 5.5 times 10 to the minus 8. So you put in the resistance, that's 0.07, the area 7.85 times 10 to the minus 7 divided by 1 meter, and that's equal to this value. And then you go along in your table and you say, well, it's not that one, not that one, not that one. It has to be tungsten. So as I said, it's a nice way to determine if you have an unknown metal that you can measure its dimensions and then measure its resistance by Ohm's law, and look it up in a table. You can determine what that unknown metal is. There are other ways to do that, but it's a nice, simple way to do so. All right, so don't forget the talk today at 4, and then you guys have that special, you know, gathering time with him. What was that, at 2:45, or y'all remember? 2:45, I think that's right. We sent out a message on the Moodle page. Y'all get those messages, Tim Majors? Dr. Cortez sent out a message on Moodle. Let us see y'all here this afternoon. It's a great opportunity for all of y'all. Not just our Tim Majors, okay? You, pre-engineering and geomatic folks, y'all are invited here. Yeah, not like those. Not like. Okay, good. All right, y'all get it, okay?
I mean,